distinguished high energy physics career, so he needs a little introduction for any physicists who are around here. But since we're having this talk at the Media Lab, we probably have a more general crowd, so I'll give a quick introduction. Even if you're not a high energy physicist, you probably heard about his famous work at CERN in the early 1980s. He's been the major innovator behind the world's first proton-antiproton collider there, the CERN PRP collider. There he led the UA1 experiment, very large at that time physics collaboration that discovered the quantum field particles that mediate the weak interaction, the W's and the Z. He won the Nobel Prize in Physics for this work, shared with Simon van der Meer, the accelerator expert, in 1984. He has been the Higgins Professor of Physics at Harvard during that time. In the early 90s, he was the Director General of CERN, played a prime role in shaping the Large Hadron Collider, the main accelerator in the next, or this decade, turning on middle of the decade, we hope.
Don't fall asleep.
And he's active in many projects since, including the Icarus proton decay, a neutrino detector under the Gran Sasso outside of Rome, and other things, including the energy amplifier, a novel and safe way of producing nuclear energy, exploiting present-day accelerator technologies. And what he's going to talk to us about today, an extrapolation of these concepts to exciting new prospects for nuclear rocketry. Professor Rubbia.
Thank you. How do you turn this thing on? It must be some switch. Just a simple switch.
That's it.
Amazing. Things tend to be complicated around here. Well, first of all, I don't know what I'm doing here. I don't know what you're doing here with me. But I had a very nice afternoon looking at all different crazy ideas and unthinkable ideas. And so I feel rather prepared to tell you about my ideas, which are not that different than one you are tossing around here. Namely, something probably will never happen, it will never be realized, but it's worth trying. I learned that 10% of your ideas come to reality. Well, it's a good coefficient. If we can do the same with this, I think we'll be in good shape. So anyway, the problem is, how about getting to Mars? Connected with it is the question whether nuclear power can be used for that. There is a group of people in Europe working quite hard on this. It's been growing. At the beginning, we have a few people now. There's about, I would say 50, 60 people working on these kind of concepts. Very general concepts. They have no practical connection for the moment, but they show the need for some new ideas. In fact, the need for new ideas is pretty evident. You know that the initial description of going to Mars has been done by von Braun in the famous early book, which he wrote in German when he was a war prisoner. And in that he described the standard mechanism to get there. There are a lot of difficulty in doing this. At the present moment, many people, including especially NASA, is trying to get there. It's not very simple, but eventually it would seem to me that this is one of the things mankind would like to do. Surely I will not be there to see that, but I think it's still fun to think about it. Now, if you wish to do this kind of jump from going to the moon, 300,000 kilometers, to going on to Mars, where the round trip is 1 billion kilometers, you have to somehow introduce some substantial change. You just cannot use the same technology over again. And the real question is, can you use, or would you like to use, this projector is not up to MIT standards. It's totally out of focus. And there's a lot of aberrations. Okay. Now, I would say up to Harvard standards. Anyway, the question is, can you use nuclear power? And I think you can certainly convince yourself nuclear power in a certain sense is interesting because it offers you 3 million times more specific energy than a chemical reaction when you burn it all. But energy is not the problem when you travel in space. What's important is in space propulsion is impulse, is momentum, is speed. And in fact, there is a famous rocket equation which determines how much stuff you can get there when you start with a certain initial mass. And this is the ratio between, it's a very simple equation which contains here the sum of the speeds that you have to add to the various operations and divides up the speed of exhaust of your gas. And that is essentially fixed by chemical fuels, which can reach a temperature of that order and provide a specific impulse of the order of 450 seconds. I don't know whether you know what specific impulse is. The specific impulse is essentially the amount of time, is measured in seconds, the amount of time over which a fuel will apply a thrust equal to its weight. So if I have a kilogram of a certain material and I burn it, that gives me a kilogram for so much time. And that time is the impulse, specific impulse. So essentially, it's if you have a kilogram of chemical fuel, it provides you a kilogram of thrust over 450 seconds. And that is essentially a specific impulse, which is proportional to the speed of exhaust. Now, the idea is, of course, to go nuclear. But the nuclear system are limited in the temperature. No, you cannot even get to the temperature of the gas. And because essentially your materials, your reactor is not standing the high temperature itself. And so you do with a thing called Nervos, I mean, the machines developed in Russia, in the United States, 900 seconds. But you do that essentially not because you have a higher temperature, but simply because you're using hydrogen. And hydrogen has a lower atomic number, so molecules move faster, and therefore you get higher speed of exhaust. Now, in other words, this is a little bit the situation. If you look at the standard, here is the stagnation temperature which your system is operating. Here is liquid hydrogen and oxygen, gives you an exhaust speed of about 4 kilometers per second. So an impulse, specific impulse, about 450. And we are talking about machines of if you like, systems, which should allow you to get to temperatures which are typically in the order between 10,000 and 15,000 degrees. This is hydrogen exposed, and the specific impulses, which are in the region between 2,500 and maybe 4,000. So we're talking about an order of magnitude improvement in the specific impulse with respect to the system based with a normal chemical system. Factor 10 in speed means a factor 100 in specific energy. Let's be clear of that. And that, of course, makes the situation much easier when you try to go to Mars. In fact, the most used trajectory is so-called minimum energy trajectory. It's called the Hohmann trajectory, the one which was used by, was proposed initially by, as I say, by the original thing, document, the book I was telling you before. The travel time is long, it's 280 days. It's essentially a free-fall trajectory, as you'll see in a minute. However, if you get there and then you want to come back, you have to make sure that the planets are in the right place. And that means that you have to add another 460 days residence. So it's a fixed trajectory which you go for a year, and stay there a year and a half, and then you come back for a year. And if you miss the opportunity, of course, things are not in the right place, and then you don't get anywhere. Now, if you want to get a little faster with this, you have to catch up on the motion of the Earth, and that, in fact, requires much higher transfer speed. Now I'll explain you what I mean. If I, now let's look at this curve here. You see here you have the, essentially represented here, the man's residence time, and you have the 640 days there, which corresponds 640 days, which corresponds to the number I gave you before. 540 days, and then you see here the various, this is the Hohmann trajectory, and then you see all these lines are possible. They are characterized, of course, by faster transfer velocity, but they give you the same residence time, which is of the order of a couple of years. If you want to go to a much shorter time mission, you have to go in, you have to make a conjunction trajectory. In other words, you have to run after the Earth, which is escaping away from you. And that implies that you have to go to much faster speeds. This is the area which is permitted. There is no other way in between. So if you have very slow motion, 5 kilometers per second, then you will be forced to do that. If you want to get to stay there for less time, you are obliged to go to speeds, transfer speeds, which are in fact quite large, 25, 30 kilometers per second. which implies, of course, speeds of your ejected gas of the same order of magnitude, and therefore you require new methods. We are talking about now missions of this type for the man, clipper missions, and missions of that type stay there for the case of transporting materials. Now, let me show you briefly how this mission can be realized. The fast mission, as I said, consists of leaving the Earth here and then running on this trajectory and getting here after 150 days on Mars. Then you stay on Mars as long as you wish, from 0 to 100 days or whatever is required. And then you decide to come back. If you want to come back, this time the Earth has gone further, so you have to catch up the Earth position. So you have to run much closer to the sun and then make a turn inwards. And that allows you to get back in something like, as I say, another 179 days. But so therefore you can close the whole thing in a year. But it requires speeds of, as I said, much higher. This is for the people which want to get there. Now, if you want to go and send equipment, as you probably need anyway, then you can follow the Hohmann trajectory, which is the one represented here. And you can see what the Hohmann trajectory is all about. It's a half a circle. You start here. You go in 280 days to Mars, 260 days. Then you have to stay all this time until such a time as the Earth is in the right position. Then you leave here. And then you go another Hohmann trajectory back 180 degrees of bang, and you hit the Earth where it belongs. That is, in fact, the long time trip. Now, we are trying to study all kinds of different missions with the potentialities of this new engine, which I'll describe in a minute. Essentially, nuclear power is going all to be used only for transplanetary trip. Classic method for landing and takes off, so you use standard fuel to get to orbit and then to come down. Air braking is being removed at this level. Air braking is an extremely complicated procedure. Imagine you arrive on Mars and then you have to get into sort of a orbit which is slowing down into the gas of Mars, and the window is very narrow. The difficulties of doing that are considerable. In fact, many of the problems in getting Mars material come from that point. We think that with people you should avoid it. The Space Station Alpha is used as a departure. And the transplant mission needs a reusable shuttle, since many trips are necessary and could be necessary. And this device will, in fact, operate on a periodicity of Earth-Mars orbits, which is 740 days. And the question is, the presence of Mars, so the man is necessary for the complexity of the task, but the harsh environment limits the stay to a short time. It's inconceivable. You can leave a person for the first time on Mars for 1.5 years, eventually to make his own fuel and come back and so forth. So he has to be able to go there to get the equipment going, but then he has to come back, and you need no sharp departure window. And then you have two kinds of missions, the clipper for fast man transit and the tug for material transportation, which can be slow. And the key, of course, all that is a higher specific impulse. Now, the present state of nuclear propulsion is not a very good state. Essentially, NERVA is the design which is now the best in town. And it's essentially a gas core fast reactor. The maximum temperature is determined by the temperature of this uranium, zirconium, niobium carbide, which has to remain solid. It runs at high pressure because the gas has to go from here to there. Here is the low temperature. Here is 3,000 degrees, so he has to warm up going through the rods of the reactors. So high operating pressure. The mass of the fuel must be large. It's 1 ton of highly enriched uranium, which has to be put into orbit in order to get criticality. But however, during the burning of all this system, only 5 grams are burnt. The rest is, it just goes there. You have to deliver it, get rid of it. And there are particularly, many people get very nervous when you put a ton of highly enriched bomb-grade uranium on orbit. Neutron leakage is very large, 10 to the 19 neutrons a second. So it makes it very hard for people to stay around. They have to be shielded, and even if they get shielded, it's not trivial. You can avoid that kind of irradiation from these fluxes. And the real problem is that essentially that the fuel is, in fact, the hottest part in the system. Now, the basic idea is, can we keep the fuel cold and the gas hot? That's what you would like to do. The answer to that is a very simple idea, which we are working on, which is direct heating by the fission fragments. Now, let me remind you that 88% of nuclear energy, due to fission, is carried by two fission fragments, the rest being additional neutrons and gamma rays. You have essentially uranium-235. You swallow a neutron. The uranium-235 starts to vibrate, to move. It separates like 2 drops of water. You get 2 little droplets. They're both positively charged, therefore they repel each other. No longer nuclear forces are present because you have severed the connection between the two. And the 200 MeV you recover is just simply the Coulomb repulsion of these 2 parts. So 2 fission fragments come off and they carry essentially 98% of the total kinetic energy. So why not use it? In addition, there are a few gammas and neutrons, but they carry only a few MeV. So most of the energy is carried by these 2 fission fragments, which are back-to-back, so to speak. Now the question is, how can you make use of that fission fragment directly? They have an enormous enthalpy inside. They represent tremendous high temperature, but you never see them in a reactor because they stop into the reactor, then you get warming up of your material. You don't get access to that beauty that nature is providing you there with. And so the question is, can you use them directly to heat up the gas? The penetration range of the fission fragments is extremely short. It's 10 microns in the fuel. And usually the energy is converted in heat inside the fuel. And now the question, can you use directly this fission fragment in order to heat the gas? And that will, of course, give you an enormous advantage, as you see in a minute. So we assume a very thin fissile deposit. Let's take a foil. Put on a foil a layer of fissionable material. And then make it thin enough so that the fission fragment can come out. And then see what happens as a function of the thickness of the foil. Here you have a plot which says 1 micron, 1 milligram per square centimeter, 10 milligrams per square centimeters. This foil are made out of uranium or americium or whatever you want. And you see here the energetic fraction of energy coming out. Obviously, you get 44% if you had 0 thickness, because 88% is fission fragment, and 44 going one direction, 44 go the other. And then when the thickness becomes bigger, you get a loss. For instance, if you have 1 micron thickness, you get 34% instead of 44. If you go to 3 microns, milligrams per square centimeter, you get 24%. Now, what are we talking about here? We are talking about 1 milligram per square centimeter, which is 0.8 microns in thickness, which is 10 grams of a meter squared surface. And we're talking about 1,100 atomic layers. This is certainly not what you call a nuclear fuel. A nuclear fuel is a very heavy material, hundreds of tons of stuff inside the system. Here is rather a radioactive source, if you like, deposited on a thin layer. Now, how do you get criticality? Now, for that, you need to do some clever things, which have to do with neutronics. Let me anticipate to you that I do succeed in having criticality with that little bit of americium. Now, let me be clear about numbers. If I take this americium, which is the largest fission cross-section known around, 5,300 barns, and you get the neutrons through that, it has 1% probability of interacting. So obviously, you like to have 100% probability of interacting to keep the reaction going, and therefore you need about a factor of 100 enhancement. So can you enhance the neutron flux with some kind of storage device so that you can get the neutrons over and over again through your americium foil and enhance this way the probability of fission? The answer is yes. Well, we've done lots of experiments at CERN on that, and in fact, this is not just a theory, it's just an experimental results. The basic idea is that you take a highly diffusing but neutron transparent medium and you let in that thing a neutron travel. Only elastic cross-section is there is no inelasticity. So this neutron moves around inside this material in the same way that, for instance, an electron moves in an argon gas. Well, the physical reason is very similar. Normally, you're talking about nuclei which are double magic. We have here the great experts for these things. And a double magic nucleus is like a noble gas. The shell is closed. So in the same way that an electron cannot capture in argon of helium, and it will go around as a free electron forever, here we are talking about the nucleus. And the neutron will not capture the nucleus because the shell is closed. And the cross-section is very small, and the result is this thing will just go around. Look here, there's a single tortuous path inside the highly diffusion medium. This is computer simulated, but this reality is not any different. The neutron is essentially stored not by like a storage ring, it's stored by diffusion. It's a random process, but effectively it keeps the neutrons together. And that is, in fact, has been showed that, in fact, 60 meters long path is wound in 35 centimeters, 1 foot in length. And this is due to the fact that this is movement random. Now, in such a storage medium, so you have a volume of this type of high purity graphite or high purity lead. In that volume, you have this phenomenon. Such a storage medium, because of multiple trials, even a very tiny amount of impurity can absorb a significant amount of capture elements. Suppose you have a ball full of water, and you put there a little bit of ink, just a little drop of ink. The whole box will have the color of the ink, even if the amount of ink is infinitesimal. Because the water is transparent, ink is highly absorptive. And sooner or later, light will find the molecule of ink and will send back the color which you put in. And same thing happens here. You have a very small amount of impurities inside this medium. It's because you go around and around and around over and over again, you'll eventually hit an impurity, and then you'll get a factor because of this multiple trial effect. And therefore, 20 grams of americium inside that box will make it critical. So now you can make devices which are critical with grams of material, not kilograms. Remember, in the NERVA, you needed 1 ton of highly fissile bomb-grade uranium. Here, with 20 grams of americium, you're critical in this continuum medium. Now, of course, you don't want to have a continuum medium. You want to have essentially the way to do this fission. So we introduce a statement which we call whole round, because it reminds of a black body, which is essentially a box which is made with high purity carbon diffuser, on which walls you put a thin layer, 1 micron, 1,000 molecular layers of americium. And then what happens, neutrons will ping pong between the walls of this container, will traverse many times the walls, and it will enhance the interaction probability, as we will see in a minute, about 100 folds. And the ultra-thin fissile layer requires a finite fission probability because of these many traversals. And the newly fissured produced neutrons, of course, will get thrown into the box, and it will start again. More precisely, we assume the empty cavity is covered with a layer. The configuration is similar to a black body radiator. And I'll let me remind you, the black body radiator, the flux is uniform independent of the shape. And the flux is determined essentially by the properties of the material, not by the geometry. The same thing will also happen here. And it's uniform independent shape of the cavity, provided, of course, it's well behaved. And therefore, it doesn't matter what the shape is, you will get this result. And also, the neutral temperature, and therefore neutron energy, will be related essentially not by the fuel, but the quality of the container. So the temperature will be fully thermalized with the temperature of your container. So you'll know very precisely what the energy neutrons you're dealing with. And of course, no neutron will come out, because being a black body, it will contain the neutrons inside. If they're inside, they're not outside. Now, the theory of enhancement can be easily done. I will not spend much time with this. It tells you that if you have any shape, and you take the reflector away, and then you put it back, and you leave the same source, and you ask to change enhancement of the flux because of the reflector on, that enhancement factor is equal to that expression, which is square root of the elastic scattering divided by the capture cross-section. Now, scattering elastic is typically 10 barns. Capture cross-section is order of millibarns. So we're talking about ratio 10 to the 4, 10 to the 5 between the two numbers. And therefore, when you take the square root, you get good results. And there are two parameters which are important here. One is the diffusion length, which means the size of your sphere of containment, in other words, the thickness of your walls that you have to use to do the job. And the second one is the enhancement factor, by how much you increase the flux. Now, if you get graphite, you get 27 centimeters diffusion length, and you get 94 enhancement. Beryllium will do fine as well. It is much smaller. It's 12 centimeters, but your enhancement factor only 73. Lithium will be completely transparent. And liquid deuterium will give an enormous advancement factor, but they also have very long length. So you'll have to build a huge device. It's not practical. And liquid hydrogen is also excluded. So essentially, you are ending up with beryllium and beryllium oxide and carbon as interesting materials. And then you try to calculate with this system criticality, and you do achieve criticality rather rapidly. Here is the thickness of the carbon wall, which is increased. Here. I increase the thickness of the carbon wall. And then here I put the K value, which means K equal 1 means criticality, means you get back as many neutrons as you made. And if I have a layer of 1 milligram per square centimeter, 1100 layers, you can see I get critical with about 250 grams per square centimeter, which means 1 meter 20 of carbon. It's a bit too much. But if I go to 3 milligrams, you see I'm already running a 75 here, grams per square centimeter, which means about 35 centimeters, which is that much. This is 22 centimeters. You haven't grown in flying over the Atlantic. That's 22 centimeters. And so it's quite a reasonably small amount of reflector. And beryllium oxide can do it fine, even better. And you can see that, indeed, criticality is obtained with layers which are only a few milligrams per square centimeter. So it is possible with this technology to make a critical reactor which will operate with a very small amount of material. Remember, 1 milligram per square centimeter is 10 grams per square meter of surface. We are talking about probably 100 square meters for this mission. So we're talking about between 5 and 10 kilograms of americium to burn, which is not very much. In fact, americium has the same property as uranium-230. Plutonium-238, which is used now on Cassini mission and was on Voyager, and usually you had more than these kilograms on it. So it's déjà vu, as one says in French. Now, the problem is which fuel element you like to use very quickly. You have to have a high fission probability, accepted a long lifetime, and not too extravagant production procedure. Now, of course, americium-242M is an ideal device. This is the cross-section. Notice the cross-section drops when the temperature goes up. This is the temperature of your whole round, 1,000 degrees, 2,000 degrees. So you're running here in this region that corresponds to those energies. Capture very high, fission very high, capture very small, big ratio between the two. Now, if the other element, which is not so bad, is plutonium-239, which is well known as a resonance here at about 0.24 electron volts. So that could be used if you were to make a container which has a high temperature, for instance, of the order of 3,000 degrees. Then in this case, you could also use plutonium, but you'll have a problem of temperature coefficient. Here is a very nice negative temperature coefficient because of this cross-section. So plutonium is the second choice. Americium is the first choice. So I've done a very complete burn-up through a reactor of this type. I'm not spending time to discuss that. Here is what happens when you take 1.4 kilograms of that americium and you burn it. You can have a fairly long burn-up. Burn-up means megawatt megawatt multiplied by day per kilogram. Means 1 kilogram will give you that many megawatt per that many days. So 1 kilogram here will give you 400 megawatts for 1 day, or 1 megawatt for 400 days, which is much bigger than what you get for a normal reactor. In a normal reactor, you get a burn-up of 20, 30 in those units. Essentially comes from the fact that the system is much more efficient when it comes to burning. For instance, here you can see during this 500 megawatt day per kilogram, the americium coming down from 1.4 kilograms to about 0.7. americium being burnt, americium-243 produced by the captures, since it's a clean situation, and here it stops because it gets below critical. And so you can get a lot of energy out of this. You can burn about half. Even more than half of your americium can go. And 3 milligrams per square centimeter layer delivers that much power. And of course, if you much longer operation, you have to remake your layer. It's a very thin layer. It can be deposited in some kind of a way. This is the whole technology has to be developed. But obviously, periodic refueling may have to be envisaged eventually. Now, how do you produce the americium very rapidly? Well, essentially, you start from americium-241, which is naturally grown in aged reactor spent fuel. Plutonium-241 has a lifetime of 14 years and goes into americium. And then you make a neutron capture. And here is explain how you do the neutron capture. And then you get an extra neutron, and you end up to 242M. 242, not M, is not stable. And so the only thing left is that one. So let's come back to the question of heating of the gas with those fission fragments. And so let's assume we have a tube. Typically, we are talking about a tube which is 2.5 meters long, 30 centimeter in diameter. This is like a fuel rod in reactor. Only a fuel rod in reactor is full of material, and the cooling is outside. Here we are talking about a fuel rod which is empty. And the fuel, instead of being deposited as a volume, is deposited as a surface inside. And then we get gas in, and then the gas goes through this thing, and it gets heated up. Let's see what happens here. You have a tube, 30 centimeter in diameter, in this particular case, 2.50 meters long. There is a thin wall, which is cooled from liquid from outside, and produces 2 watts per square centimeter of heat, and produces 3.95 megawatts of power. This rod is immersed, as you will see, in a lithium bath. On this wall, there is americium, 3 milligrams per square millimeter. The total mass is 71 grams, so it's not very much. And there is a little bit of gas flowing through the system, 1.2 grams per second, so 58 microgram per square centimeter, so it's very slow flow gas. The whole damn thing is taking 1 gram of gas per second. And the gas is flowing very slowly. It leaves the wall, it departs from the wall. When it departs from the wall, it warms up. And when it comes down here, you will see from exact calculation, it has temperatures of the order of 10,000, 15,000 degrees. And in fact, it's, the wall are cold, and the gas is hot. So it's maintained, this is my statement, maintained the top foil reasonable temperature, cooling from outside, so the wall, the sheet, the foil, and the gas is moving from the wall, and when it gets in, it gets hot. And by the time it comes down there, it goes between 10,000 and 15,000 degrees. And see now which limits there are and how can you get there. Now, temperature limitation due to mechanical strength of the nuclear fuel are removed because the fuel is cold and the gas is hot. Now, there are several gifts of nature in here which are worth reminding you. First of all, the range of the fission fragments exiting from 3 milligram materials be calculated for the actual Z and A distribution. And it turns out that the specific ionization per unit of mass is in hydrogen much greater than the one in americium. There is almost a factor 20 higher specific ionization loss in hydrogen with respect to americium. What is due to that for? What's the cause of that? The cause to that is the following, that ionization losses only work when the particle traveling is faster than the electron bound in the atom. And the fission fragment is beta equal 0.04, 4%. So many of the electrons bound in the americium foil have a speed which is higher than the speed of the fission fragments, and therefore they are essentially not participating in the ionization loss. If you take hydrogen, well, the velocity is 1 over alpha. And therefore, it's much smaller than the velocity of the fission fragment, so that you have a higher ionization losses. You can see here that the range of these fission fragments is about 10 microns in, as I said, in americium, but it's less than 0.5 micron in gas. So you get an enhancement of a factor 20 in ionization losses in the gas. which is in fact extremely important. And so even half a milligram per square centimeter of gas will absorb the fission fragment completely. So you can operate with very low pressure. Actually, in reality, the fission fragment goes in all possible directions, so the range is only the upper limit to the travel. So let me take two infinite planes coated with americium, defining a volume filled with hydrogen gas. So you have two planes here. And these two planes are now filled with gas. And the fission fragment traversing it, the thickness is half a milligram per square centimeter, so it's about 20 centimeters, 3 atmospheres, just to get ourselves understood, even high temperature. And then you have, this is the kind of heat produced by the wall to the left. This is the kind of heat produced by the wall to the right. And when you put them together, you get a reasonably flat distribution. The important number here is this very simple one-dimensional this drawing, which in fact will be is worse than the case of the tube, which I'll discuss in 2 dimensions in a minute. You get with 400 watts per square centimeter on this foil, you get about half a megawatt per gram in the gas. Now, a megawatt is an enormous power. A megawatt in a gram is just putting a megawatt on a mosquito. And obviously, if you put a megawatt on a mosquito, you will give it it will fry very rapidly. And therefore, the idea is that you can keep the foil under very normal condition of a reactor, but get a real hell inside the gas. As I said, you can get a megawatt per gram with hundreds of watts per square centimeter on the wall. Now, this whole thing is played the following way. Here you have, in this curve here, the watts. Unfortunately, it's hard to see. I cannot even see myself. I wonder whether you can read yourself over there. Now, here you have 1 megawatt per gram, 100 kilowatt per gram, 10 megawatts per gram. And here you have foil surface power density, watts per square centimeter, 100 watts per square centimeter, 400 watts per square centimeter, 800 watts per square centimeter. This is the kind of region in which a normal reactor is operating. And you can see that you can go all the way up to about a megawatt per gram in the gas with reasonable heating on the walls. And that is, of course, transformed into temperature through the enthalpy diagram for hydrogen, where you have, here you have enthalpy, 10 to the 5, 10 to the 6. This is in joule per gram. And you have temperature here, 10 to the 3, 10 to the 4, 4, 10 to the 4. Now, you have to pay little attention to this curve. Here, up to 3,000 degrees, the enthalpy is rising linearly. This is a perfect gas. Enthalpy, specific heat is constant. It's essentially the temperature of a single hydrogen molecules. At about 3,000 degrees, the molecule dissociates, becomes atom. Then you get the enthalpy to do the destruction. That is like a chemical reaction. You put energy in it, eventually come back after you've done it. And then you start with another slope, which is twice as sharp, because you have twice as many atoms there, and therefore you have a higher specific heat contained for a given gas. And then you get to about 10,000 degrees, and when you get to 10,000 degrees, the gas gets ionized, and then you are getting the 13 electron volts of ionization. Remember, 10,000 degrees Kelvin is 1 electron volt. But here we are talking about recovering something like of the order of 10 electron volts. And therefore, the enthalpy grows tremendously, even if the temperature doesn't go very high. And essentially, you are now talking about enthalpy, joule per gram, is equal to power, watts per gram, times dwell time in which you are under exposure, time gas takes to come out of the container. Typically, we're talking about several seconds in this machine. So we are talking about seconds multiply megawatt per gram equal to gigajoule per gram. Gigajoule per gram is right here. So we're talking about temperature 10,000, 15,000 degrees. And while in NERVA you have fast motion, short dwell. Here you have slow motion, long dwell. And this gives you the impulse which you can get with 10,000 degrees. You're about 25 kilometers a second exhaust speed and about 3,000 in specific impulse. How much time do I have left?
20 minutes.
20 minutes, okay, fine. Now, then, to do that more clearly, we are talking about parameters of this tube, 20 centimeter radius, 2.5 meters in length. And we are talking about 1,000 degrees for the wall, final temperature in the gas of 10,000 degrees. And we are talking a very small amount of gas coming through. We are talking about essentially speed of the gas of 0.75 centimeter per second at the beginning, 3.5 grams per second through the system. And this is the heating stage. Then you have an expansion cone, which brings you down to about 2,500 in specific impulse, or 25,000 meters per second. And with this thermodynamical efficiency, about 70%. Now, there is one technical point which I quickly like to mention, which is a substantial limitation to this method, to this system, which are the radiative losses of the gas which gets heated. When the gas gets very hot, it starts to radiate, emits power away. Eventually, if the power radiates is more than the fission power coming in, you are in trouble. Essentially, it's a lot of work to calculate all this. There are type of losses, line, band, continuum. Now remember that we only have atomic hydrogen, therefore the molecular levels are not there. And essentially you are talking about theoretical hydrogen is beta book, 1, 2 electrons in the handbook de physique. Since then we know all the numbers, so all the calculation can be done very precisely. And it turns out that the radiated power there is essentially the line emission is quickly absorbed. Essentially the line looks black because of the absorption is in fact quite strong near the line, and therefore you don't have essentially, it's like the sun. When you look at the sun, you see the sun, the plasma of the sun, you see the lines dark. You don't see the light coming out of it, so there is no radiation from the lines. There is, however, a substantial band emission, which is there. It's been all calculated. I'm not going to get into details with this. Essentially, it turns out that what happens is that the light is growing with the temperature of the gas. And this is frequency, and this is the power after a certain finite distance. And it's becoming a lamp, a big lamp. And here is the surviving radiated power as a function of the distance of the gas. This is about 1 centimeter of gas at 3 atmospheres. So most of the light emitted by the band is absorbed immediately in the region where it's emitted, and therefore it contributes only to heat conductivity. But there is a substantial component, which is this flat line here, which is in fact having a very constant, a very long attenuation path, and this is the light you can see on the walls itself. This is all taken into account in the calculation, and essentially it tells you that up to about 10,000 or 12,000 degrees you can operate, and above that you have a problem of radiation which you have to solve. The other question which is important is the recombination of the hydrogen. The hydrogen is starting from being, well, let me show you here the curves, which is probably the best way of showing it. The hydrogen starts as a molecule. This is this line here is a function of temperature. This is logarithmic scale. Very quickly becomes an atom, and then about 10,000 degrees it starts to ionize. Here, for instance, 3 atmospheres. Here, 10,000 degrees starts to ionize, and at 15,000 degrees is about 50% ionized. So essentially, what happens is that you're dominated with atomic gas, and above a certain value, you're also dominated by plasma, which is substantially ionized. The plasma, the recombination electron proton, in other words, the combination of the plasma, it's a very fast reaction because it's gamma plus neutral hydrogen equal to electron plus proton. It's a perfectly large cross-section. The recombination molecule to atom, it's very slow. Remember, two atoms cannot make a molecule because there is no momentum energy conservation. So a single collision of 2 atoms will never make a molecule because they have to emit a gamma, and the gamma is not there at those temperatures. And therefore, the thing is metastable. You remember the so-called hydrogen torch, plasma torch, in which you take molecular hydrogen and you make it atomic hydrogen, and then you throw it on the wall, and when it hits the wall, it becomes molecular again because it finds the recoil. and therefore it gives you heat, and in fact you can melt a lot of stuff in this way. Now that is essentially what's happening in our case here. However, as I showed at the beginning, first of all, the gas is essentially, therefore our gas is frozen. In other words, we expected this gas to come out essentially as an atomic gas. However, atomic gas means the A is 1 instead of being 2. And therefore you pick up a square root of 2 in the number of the speed of your gas. And therefore, although you lose part of the energy because you're dealing with an atomic system rather than being a molecular system, the effect on the specific impulses, as shown in the first transparency, which I hope I can find again here, is quite small, essentially because of the fact that the gas is reducing its A. And so we have essentially, this gas comes out very cold. When you hit the problem of the funnel is not a very important point. Now, since we are in a computer science here, let me tell you some computer simulation. So I'll feel you a little bit more at home. So what we've done, we have developed a lot of programs which do the following. This is doing fluid dynamics calculation. This is making the fission fragment transport heat release. This is worrying about radiative effects of the gas. And this guy here is combining the energy losses and energy radiation to close the loop with the program, which is the program on fluid dynamics. So this is a fluid dynamics program. Then it goes into a heating from fission fragment with the neutronics providing the supply. Radiation, you lose power, you make power, you take a power balance and you put it back and you make recurrent calculations. And then we have done several models here with a typical 20 centimeter, 2.5 meters machine. Simulation rather sophisticated. We have hydrogen inflow 100 Kelvin, which is in fact uniformly distributed. And I mean, this thing is really horrible. And then you get essentially various intensity of flow. Let me show you some results. Here is, we are increasing the temperature of the heater. This is half of the cylinder. You can see there's another half coming on the other side. So you start from the wall here, and when you move on, you heat up the gas slowly until the gas gets very hot, and then eventually down here the gas is the hottest, and it comes out from the funnel. You say the same thing here, case number 3, which is the one we consider the most appropriate, and you do get about 10,000 degrees out of that, and you do get essentially all the gas is nicely hot at the end. So the fluid dynamics works extremely well in this story. Actually, you can see here global power deposition and temperatures, and you can see in fact that these kind of calculations are perfectly adequate. So we have a good fluid dynamic model of this. The heating process of the fission fragment in the 2 dimensions is quite remarkable. Here we had 200 watts per square centimeter on the tube, and here we are collecting here 900 watts per milligram, so we are collecting 900 kilowatts, so 1 megawatt per gram of the gas. And you see here is the radius of the container. In the central part is very uniform. These 2 lines correspond to the top and the bottom, where there is no coverage. One hand because you're going out into the nozzle, the top because there is nothing on the top. The americium is only deposited to the sides. If you were to increase the pressure from 2 atmospheres to 12 atmospheres, then you will observe this. Your fission fragment will just stop before they get to the center, and only the sides is heated. A few more minutes left. I can describe you here some of the design consideration. I was saying this is the kind of tubes we're talking about, and then this many tubes are inserted inside a box. So let's look at this. This is a realistic engine. This will carry Emission, according to what Asi is calculating, over to Mars and back again in the way I was describing you before. It's made essentially by a series of tubes, 2.5 meters long. Those tubes are equivalent to the fuel elements. They have on the bottom the nozzle, and therefore they can be clamped on a baseline, if you like. They are immersed inside a sea of lithium, liquid lithium with bath, which is the coolant, and this works as a boiling lithium reactor, if you like. The lithium is all around here, and it touches the outside of those tubes so that the outside wall is cooled with this lithium, and the lithium is traveling all over here. There are control bars coming into the whole realm, so you take away the neutrons to control the process. The system is essentially a lithium-cooled system. You have lithium which boils. Lithium becomes vapor. The vapor lithium goes to the panels, which are the cooling panels. There it condenses again, it becomes liquid, and then is recollected and put back again. So it operates at constant temperature, but there is the heating, the fraction of the heat which is used by the boil-off heat, which is used for cooling. These are the numbers indicated here. We are talking about thrust power 30 megawatt. The overall thrust efficiency is 17%, 177 megawatts of consumption total. Exhaust speed 35 kilometers per second. Propellant flow is 50 grams of hydrogen per second. The thrust is about 2,000 newtons. The foil power density is 2 watts per square centimeters. There are 88 square meters of americium. And this machine will run with 2.4 kilograms of americium, so very little. And the refueling time will be every 9 days. Every 9 days you go in there, you just put new tubes or whatever to get going. So we're talking about a few kilograms of material, and you can get 9 days. Over 9 days you can get this power. This is sufficient to compound the mission. I mean, you will do these things, refueling not during the mission, in the periods in which you are recovering. So it's quantized in a proper way. The other way of doing it would be to do a Katyusha type of thing. In other words, each tube is blowing separately, but that is a question of the technical design. Now, obviously, this is an idea. As I said, all ideas have a chance of not to work. This is certainly a very high probability not to work, but it's still fun worrying about. First of all, the behavior of the americium under extensive exposure to hydrogen is the problem. The good news is that the Nerva engine also has hydrogen and also has a fuel. It's not americium, it's uranium, but they're very similar chemically, which is in contact with hydrogen at high temperature, and it doesn't go away. The bad news, of course, is the deposition is thin. In the case of Nerva, you got a piece of solid rock. The other question, radiative loss for the hot gas, is still some work to do, experimental work to do. Below 10,000 degrees, there is essentially very little, no radiation. If you want to go above that, the calculation one thing, the experiments are the other. You've got to do something about that. Now, hydrodynamic calculation, obviously, is the more important point. And there we have questions like transformation in the nozzle from the plasma to the atom and the atom to the molecule. When it cools down, you have to understand what it does. It's frozen flow, etc. And also, other possibilities are, instead of using hydrogen, you could use any other material. And one interesting material to use, it would be lithium hydride. Lithium hydride is a material which is solid at 650 degrees, boils, becomes liquid, and then you can throw it into the system. It looks like a solid fuel instead of being a liquid fuel from a practical point of view, so you get less thrust, but you do have the advantage not to go around with enormous dewars. And eventually, in a 5 to 10 years period, we'll have to do some testing. So we're talking about a test facility which should be large enough to test fully, or maybe a few final tubes. Now, in Italy, and in particular also in America, everywhere, every time you say a reactor, everybody gets really up in arms, says, my God, you don't want to do it, etc., etc. So we decided that we could also do it with a subcritical facility. It can be done. The whole round can be fed with neutrons, also from an accelerator. And this type of thing will allow you also to produce americium after that, and essentially would allow us to go the faster track. And the idea is to take one of these tubes, as I was indicating you, 2.5 meters long and 40 centimeter diameter, And that will give you about a megawatt of power. And the exhaust speed will be 35 kilometers a second. And you can put that in a whole round, which can be made, for instance, with D2O initially. Eventually, then you can go to lithium. And the supply of neutron will be provided by an accelerator, which will give you some neutrons in there. And then you blow this horn in this tube, and then you collect the gas. There's not much gas, only 1.232 grams per second. So you can pump it, you can freeze it, and you can recycle. So that could be a model of taking one of these tubes to make it work. And then if you understand one of those tubes, you can do more. Now, obviously, we were talking about engines capable of doing manned mission, but obviously you don't have to do that. You can use one tube of smaller devices to carry also instrumented missions. For instance, there are lots of instrumented missions which you could do with 10, 20 tons of initial load, rather than using the 100, 150 tons which are required to get onto with a man on Mars. And there is a lot kind of interesting things like the story about Europa and so forth and so on. I mean, in other words, to get into this thing with this device. Remember, this thing is very modest here. You only have 100 grams. This device, 80 grams of americium and 1.4 grams per second of gas, but still gives you about a megawatt of thrust power. So it's quite a device. You don't have to go to the gigantic device with a Superman getting there to start. A thing like that is certainly already interesting enough for a device. It's extremely simple. There are no moving parts. There are no high pressures. It's essentially a leaky tube in which you put a little gas and you get your fission fragments into it. So it looks like quite a cute thing to try. Well, I finished with that. Thank you. Not much. The power going to the wall is below 10,000 degrees. It's very small. Oh, definitely, definitely. It's all included. I have a curve here. You see, I have a curve here, Arthur. Here, we have a heating power of 1.5 megawatts. And then this is the power going onto the walls. Integrated power watts. And on the tube, and you see that if you go to 10,000 degrees, you're about 40 kilowatts. So you get 40 kilowatts. There's a lamp of 40 kilowatts. And, but the power of the fission fragment is 1.5 megawatts. So in fact, the amount of power coming out is only core, only the red central region. See, it rises extremely rapidly with temperature. At 8,000 degrees, there is nothing. So only the last little bit is emittive. So you will see a very luminous core starting 8,000 degrees and going up to 10,000. That region there will be quite a light. But that volume is a small fraction of the total because most of the work which you do at lower temperatures, because there you pay the enthalpy of separating the atom, the molecule to the atom. And that is where most of the work is. And then, therefore, there is a relatively little gas, which is very hot in it. And that justifies this thing. But this is a perfectly legitimate and exact calculation using the correct cross-section for hydrogen, the atomic modes, and et cetera, with a complete simulation of hydro, et cetera, including all kind of sophistications. It requires parallel computing. It's a big program. It takes 20, 30 hours to compute. And I think it, as far as computing is concerned, is the state of the art. Now, of course, reality may be different.
How do you throttle it?
What?
How do you throttle the engine? You change just the gas flow?
First of all, this thing has very strong negative coefficient, temperature coefficient. Therefore, by putting the position of your control rods, you somehow define the temperature. Define the temperature of your device, because if you when it cools down, it gets to higher cross section, and therefore K grows. But then when it gets hot, it stops, etc., etc. So it's essentially there is a very, very strong negative temperature coefficient, and indeed you can write the temperature on your control rods, and depending how deeply you're putting in and out, you will fix the temperature operation of the system. So you can control the amount of power. Now the second variable you have is the amount of gas you're getting in. And now if you put in a lot of gas, it will go in and out rapidly, and therefore it will change substantially the operation. So the second control you have is that one. With the two things, you can, in fact, quite well cover thrust factors about a factor 10. However, when you look at the mission, you realize that this kind of variable thrust or variable specific impulse, whatever you want, it's more a sophistication for mathematicians than reality. When you get there, you go to a flat on period. And so I would expect that 95% or 99% of the time the thing will run on and off. What you do in a mission, you start first of all pushing it, and then when you get close to Mars, you have to turn around, and then you have to slow down to catch the system. So you have, but the period in which the engine is on and off, but essentially you don't have that much room for. Doesn't seem necessary to have high sophistication in the way the engine is running. You're not running in downtown Boston. And this is only for the transplanetary travel. Then when you want to, then you stay on you have essentially two standby orbit. One is the present space station, and the other one should be identical over Mars. And then you have transfer between the two. And most of it is reusable, by the way. Yes, sir.
A couple of questions about the heat to the walls. One, I wasn't clear whether the calculation included the convective heat transfer or only the nuclear direct heating. And
convective transfer, what do you mean? Yes.
The ordinary process of transferring heat from a gas to...
Yeah, well, the heat to conductivity and radiation conductivity are in the program. But actually, the conductivity of gas, this doesn't seem to be very important, very strong. What happens, the gas starts moving very slowly from the wall and then moves slowly towards the center, warming up. It takes about 1 second to go through the system. So it's a very, very slow motion. And the corrections coming from heat conductivity are not that important. In the long run, they are irrelevant except for the heat which goes to the wall. Because if inside the gas there is some heat exchange, it doesn't matter. The important thing is that you deliver the power inside the gas.
And the second question was the lithium cools the wall, and who cools the lithium? Didn't catch that.
I have been a little bit too quick probably on that, but I'm very happy to come back to it. What I was saying here is that we have a we have here a liquid lithium inside this device, which is here, and the lithium boils. Boiling of lithium produces some, like in a boiling water reactor, a boiling lithium reactor, so you get vapor of lithium. The lithium vapor is separated here. Here you separate vapor from liquid. The rest of the liquid comes back and circulates again into this in this volume, and the gas is sent to the irradiation panels, which are panels put all around the engine, and which they are operating about 1200 degrees, so they give you about 300 kilowatts per square meter, something like that. So they are about 1,000 square meters, something like that. And they are essentially foils in which the lithium enters as a gas. It condenses on these tubes, and then it comes back in terms of liquid back. The problem we have seen there is that meteorites may punch a hole into those walls. It may happen, and therefore you have to have a system in which the system is sufficiently segmented. Ideally, you have some kind of valves or whatever which avoid that kind of phenomenon. But at the temperature of 1200 degrees, to get rid of the heat is not an important problem. What?
Don't you need some electricity on emission?
Yeah, of course. I mean, this is absolutely right. You are in this present approximation. I'm saying this heat is waste. In reality, having 1,000 degrees temperature, it's not a bad thing to use to do all kinds of different things with it. And therefore, all the support, energy and transmission, whatever, it will all be taken out of that. And by the way, there are very nice devices which are developed apparently nowadays in Russia, which are thermionic devices. They're using a very narrow gap, and they put a thermionic emission effects, and you make a tyrotron essentially. You put gas in there so that you can get the space charge is eliminated, and they take a lot of power out of those things. They get this would be ideal for this device. So you will have 1,000 degrees. It's like a cathode of a vacuum tube, and it will emit electrons, and those electrons will give you a 1 volt potential or something like that. And then you will be able to recover a fraction of that energy directly on the panels in form of secondary emission thermionic type of devices. There is plenty of possibility using that heat. It's not just garbage. There was some question there. Yes, sir.
Yeah. What would happen to the fission fragment? Would it left on?
I couldn't hear you.
What would happen to the fission fragment? Would it be left on chamber, or you would go with the hydrogen gas?
What's that?
What happens to the fission fragment?
Okay, very good question. First of all, Professor Kerman will tell me that the fission fragments are necessary, because without fission fragment there are no delayed neutrons. And without delayed neutrons there is no reactor, because the reactor is a prompt. So a certain fraction of the fission fragment have to stay inside the system. If you throw them all out, you will have no possibility of controlling the reactor. Now, in reality, as I said to you, about the 34% of the energy is, in fact, carried from the gas into the from the fission fragment into the gas. The remaining 2/3 of the fission fragments are, in fact, staying inside the material. In principle, they should half will stay if the foil is infinitely thin, but if it's a little thicker, you stop more of them. So about half of the fission fragments will stay inside, implanted inside your foil, just as they do in a normal fuel. In a normal fuel reactor, they stay there, and they eventually get eliminated. The other half will go into the gas and will obviously be exhausted in the environment. Now, obviously, that is maybe a problem. Indeed, it's not a problem, because we are talking about a relatively small amount of fuel. We are talking about a few kilograms over the billion kilometers of transfer between the Earth and Mars and return. We are talking about a very high speed of emission, and the kind of radioactivity garbage there is in the open space, it's so large anyway that this kind of fission fragment, nobody will even be able to detect them in a way. So I don't think they represent a problem. By the way, also in Nerva, they're thrown out. You know, this thing goes off at 35 kilometers a second. It's 100,000 kilometers an hour. That's the speed at which this thing comes out.
But the Martians will be able to detect us from the fission fragment.
Right, right. Then we'll. Good. Was another question here? Yes, sir.
Yeah, I thought one of the main problems with open cycle systems like this is not so much that the fission fragments contaminate whatever, since we're talking about space, but the fission fragments actually lower the specific impulse of the system.
No, because they're very few. Because you see, the average temperature of the gas, is 10,000 degrees. That means every atom has 1 electron volt. The fission fragment is providing you 100 MeV. Okay, takes a lot of 1 electron volt atoms for 100 MeV kinetic energy. There's a factor 10 to the 8. So the one fission fragment will heat 10 to the 8 hydrogen atoms, and energy conservation. And so you'll see that you have 1 electron volt outside there, but indeed you have 10 to the 8 to start with. So it's 10 to the 8 to 1, 10 to the 7 to 1, something like that. So there will be 1 in 10 to the 7, 1 in 10 to the 8, which will be a fission fragment. And that's a very small number. It doesn't contribute. There are ideas. People have proposed to use fission fragment directly as propulsion systems. There are ideas in which you take the fission fragment, take the foil, don't put anything and let the fission fragment go into space. That will give you a push, obviously. The problem is that the fission fragment will have a very small push because they have a very high speed, and therefore they will give you a very high specific impulse. They will be ideal, for instance, to go to outside the solar system. If you wanted to go to a nearby sun, you will need the fission fragment propulsion. In this case, you will not put the hydrogen. You will just make the system and let the fission fragment come out. They will come up with a speed of 4% of the speed of light, and therefore it will be optimal when your rocket will go to 4% the speed of light. So it will make in 20 times 20 times the light distance, so you'll get there. So if you have 5 light years, 5 times 20, in 100 years, you'll get to the neighboring sun. You can make a mission of that type. For that case, you will need the fission fragment directly. It would work in the same way. I mean, there's nothing wrong with that. You will not put hydrogen, let them out. In fact, some other people have even thought about it in the past, using sources and so forth, californium and so forth. That would be good if you were to have much higher speeds. But here you want to have a relatively modest job. You want to fill the gap between normal chemical and this kind of advanced propulsions. So you need a lot of stuff with a relatively small speed to get sufficient thrust with a modest power. Because the power goes like mv squared. The thrust goes mv. So if you have a very high speed, for a given power, you get a little thrust. But you get high quality thrust. So eventually you could do that. You just run your system with empty. Let the fission fragment go, and then you will get a very tiny little thrust, but it will go for, will be on even if your spacecraft gets speeds which are very close to the one speed of light. It's somewhere in between that and antimatter, if you like. It's, in my view, but it's very simple as an apparatus because you just have a layer which emits fission fragment in space. So it can be very reliable. You can think of having the damn thing running for a long time. Yes, sir.
I'm still worried about the heating of the wall. You say about 1/2 to 2/3 of the fission fragments stay in the wall, but only about 3% of the energy apparently stays in the wall.
Who said that? Who said that? No.
Well, there were 1.5 megawatt in the hydrogen and 40 kilowatt in the...
It's a different power. This is the power which is coming back because of radiation. There was a question Arthur Kerman had. What happens of the light emitted by the hot plasma, how much there is there, and how much is the effect on the walls? And that is a small effect.
Well, let me change the question then. How much is the total amount of heat deposited on the wall per unit area?
Well, I was explaining you that I am taking the same kind of situation as a normal reactor. Let's take a normal reactor. In a normal reactor, you have a fuel rod. The fuel rod produces about 200 or 300 watts per square centimeter. That rod is immersed inside the sodium, for instance, superphenix, or other liquid if you have different machines, and this liquid takes away the heat, correct? Now, imagine that that rod now is changed. I remove the inside, the fuel which is inside, and I replace it with an empty tube, in which I put some hydrogen, that's my business, and I transform the fuel from being solid all the way to the center, just to be on the periphery. If I put that fuel on the periphery, my cooling will go much better because I will have no conductivity problem inside the fuel itself, rod. But the amount of power per unit of surface is the same as the previous one. So in the same way I was able to run a reactor with that power density, I'm able to run this quote-unquote reactor with empty rods. I empty the rods, I go from two-dimensional to three-dimensional to surface. You follow me? So all the thermodynamics is already solved by any ordinary reactor guy. I will calculate my own engine in such a way that if I have no hydrogen, is turn off the hydrogen accidentally, and therefore if all the power goes to the fission fragment, I will have enough cooling to make it work, as it is in a normal reactor, where all the power goes into fission fragment and becomes heating. So you see, there is a continuity between building a reactor and building this machine. If any, when you make this machine, you are better off than you are in a reactor. What?
You have cooling inside the rock. Gas is cooling.
No, but I forget about that. I design the machine in such a way that even if there is no gas, I don't want to have a meltdown. And this is famous 200 watts per square centimeter, which is a normal power in superphénix, in Phoenix, in other machines which are around in the world, cooled with metal. So, you know, it's like you replace your rod with an empty rod.
So in the end, half of the power has to be radiated away? Is that what you're saying?
I am designing the machine in such a way that the full power can be dissipated away and still the machine works. Because if I switch off the hydrogen, then all the fission fragment will return inside the layer on the other side. And I have to be prepared for that.
I think I see where the confusion is.
Hmm?
You're talking about fission fragments and saying if 1/3 of them heats the gas to these enormous energies, then the other 2/3 should be heating the walls at these enormous temperatures as well. Is that what you're saying?
No.
No, per fission, you have about the same amount of energy. So if 2/3 of them go one way, 2/3 of the power goes that way.
No, but the point is that you stop in the gas 20 times more efficiently. The point is that the gas is very viscous, is very effective in stopping the fission fragments, while the others is not. You see the difference in range is a factor 20 to 1. So the power density in the gas is very high. This is why you get a megawatt per gram with 200 watts per square centimeter on the surface. Yes, sir.
What are the typical residence times for the neutrons in the diffractor?
Can you hear you?
What are the typical residence times for the neutrons in the diffractive medium outside?
In this thing, they last about 30, 50 milliseconds. They are acoustic. You could hear them coming and going. You know, they just go for you know, they go about 300 or 400 times back and forth. They're traveling 1 kilometer per second. That's the thermal speed. So 1,000 meters per second. Sorry, 1,000 meters per second, right? Is the speed of neutrons, right? They go 60 meters. They go 3 meters each crossing. So 100 times is 300 meters. So 1,000 meters per second, 300 meters is about 0.3 seconds. So those neutrons stay forever. They stay for, you could hear it. You get the neutron in, and when it comes out, you say bingo, bingo. You can hear the two sounds. You should be able to see the two sounds separately, like in the sonar.
One last question.
Yes?
Could you review the, I may have put it slightly late for this, the mission profile given this engine? Are you still talking about home and transport workers or something that comes faster?
No. I try to answer. This is a good question. I think it's important it's clarified. I don't believe you can send a man on a Holman trajectory, 1 year to get there, 700 days, 640 days to wait for the good time, and then another year to come back. Besides, if he's American, every year he has to pay his taxes. That's the law. So he needs a special waiver. So anyway, evidently, this is not possible. In the Mission 3.0 of NASA, one assumes that you get there and you manufacture your own fuel there. So you get there for the first time in your life in conditions which are extremely harsh. You stay there for 600 days, which is 2 years, and in the little boxes. And then you have to make your own fuel. And if you need an extra gasket, spare parts will be hard to find. Correct? And then you come back, you stay another, and by the way, also there is a fundamental point which has to do with radiation. We have calculated the amount of radiation dose that you get by staying there, and it's very large. The fact that Mars is a very thin amount of air, it enhances the radiation because you get a maximum of the cosmic rays. And even if you go underground, you have to go underground something like 5 or 10 meters before you can get rid of the whole thing. And in fact, you get sky shine from the wall, from the soil. You sit there, all these cosmic rays go inside the soil, and then they come back, nice neutrons, which you get into your body, and so forth. So the dose, it's enormous. It's larger than the Chernobyl fireman. So the risk of a very long trip is primarily radiation hazard, in my view. And in my view, it's very much at the limit of what you can accept. 50% survival probability, stuff like that. Already on the moon, there was a lot of radiation given to these astronauts. People don't underline that, but that was a very short trip. Here we're talking about 3 years, 4 years, 5 years away from home. Now, obviously, the question is, do you need a man over there? In my view, for many things, you don't need a man. You can send a test, a device, etc. But those machinery will be so complicated that you need somebody to go and fix them. Look at the Hubble telescope. If you don't send a guy up there to change the window, it will not be possible to repair it. And similar thing will happen also over to Mars. So Mars is a planet. It's a very complicated thing. You have to do enormous amount of exploration to do that. Lots of experiments, stable studies, and not just touch and go. It's not like it's the real planet with a complicated story and so forth and so on, etc. So you will have a lot of equipment there, which will run more or less automatically, but it will need now and then a man to fix it, to install it, to modify it, etc. So you need presence of man in space, but not total presence, only in a short period of time. So we are devising a mission in which you go there on a very short track. You go there in 100, 150 days. You stay there for a limited period of time with no time window. So if today you cannot do it, if it's a dust tempest or whatever, you can go back tomorrow. And then you come back, and then this you can do with the periodicity, which is the 740 days, which is the super periodicity of the system. And in the meantime, you send a cargo, which can take all the time to get there, and with a lot of stuff, a lot of equipment, which you install and you operate. So the idea is that you have cargoes which bring the largest amount of material you can. The specific impulse is useful because it increases the efficiency of the payload. And you get there with a substantial payload, and then you leave it there. Essentially, it's dead. It never comes back. The engine, the tugger, comes back empty, and the rest stays there. And then you send a human mission periodically to update the system, to improve the system, to collect the data, to fix whatever is to be fixed, to take the decision, but on a short period of time. And that implies about 50, 100 days to stay there, and 150 days to come back and forth. This is possible with this kind of engines. It's impossible with the chemical. That von Braun has already proven. It's marginally possible, probably impossible as well, also with nervous. The other problem is also the question of putting in space amount of fissionable material. Here, americium is very similar to plutonium-238. As I said, americium is 1/3 of the toxicity of plutonium-238, roughly the same lifetime. And so we are bringing in a hazard which is comparable to this generator already used, to put a ton of highly fissile material in orbit. Well, there are presumably reactors in orbit, but they belong to security, classified activities of some unspecified country. But in practice, if you make a thing like this, you can't go with a ton of uranium and hope the people will let you get away with it.
I'd love to entertain more questions, but we have to close things down. Let's thank our speaker again.
Thank you.